Hello everyone, my name is Hazem Bukhari. My teammates are Mayur and Pranav. We're being mentored by Katerina Shabu-Veliko and we're being advised by Mikhail R- Romani. So EEG signals are known for having low signal to noise ratio, meaning they're very noisy, and thus we have to develop techniques to extract the useful information from all the noise. Classically, this is being done by using handcrafted features or filtering techniques that are task specific, which means they're not very generalizable among different tasks. So, to this end, in this work, we're introducing hybrid EEG, which is a foundation model for EEG signals that aim to extract generalizable representation that can be used for any downstream task. We have been inspired by the audio domain Hubert and Wave2Vic, which have shown to perform very competitively compared to specialized models. And to show the effectiveness of our representation, we're going to benchmark it against three baselines on the P300 task. For training Hubert, we use the TUH dataset, which contains over 64,000 EEG recordings spanning over 10,000 unique subjects. We limit the recording to 1 hour long for each of the 10,000 plus subjects. For the downstream task, we're using BNCI dataset, which only have 8 subjects and 16 seconds of recording for each one of them. For the pre-processing, the machine learning pipeline uses band filters followed by notch and then ICA to remove the noise. For the graph neural network, only band filter, and deep learning and Hubert uses instance normalization. For the baseline EEG net, it is a 1D convolutional neural network that tries to learn both temporal and spatial features across multiple EEG channels. For the graph neural network, we extract lag for each of the channels, and then each lag we compute the correlation matrix between each lag and the original signal for each channel, and then the extracted features are flattened. Pass to K means to create two clusters where we compute the adjacency matrices, which we finally feed to our graph neural network. For our SVM, we calculate 7 time domain features and 4 frequency domain features, and then we concatenate all of them for each channel, passing them to our SVM. These are the results, and we can clearly see that the deep learning models can learn more useful representation than the other two baselines that we have. For Hubert, EEG is a self-supervised model, meaning that it generates its own label by converting the raw signal into MFCC and then splitting them into 25 millisecond tokens, then using k-means to cluster them, where each cluster is one label. During training, it masks 50% of the generated tokens by our CNN, and then it tries to predict the label for these masked token and then perform cross entropy across all the labels. For the loss, the masked token prediction, we mask a portion of our CNN tokens, predict the label for those, and then perform cross entropy over the masked and unmasked labels. For our downstream task, since we don't have a specific one for Hubert, we used P300 as our downstream task and accuracy as our metric. These are the results from our training. We're collapsing all the channels into one by summing all of them. As we can see, the number of clusters can affect the performance of Hubert greatly. So in conclusion, Hubert can be adapted for EEG signal with minimum modification, but it is very sensitive to hyperparameters, and it is tricky to tell if the excited representation are useful or not without performing downstream task. And final report, we will perform evaluation downstream task and experiment with single channel. So future direction, using 2D convolution instead of 1D for multi-channel, using spectrogram instead of MFCC for feature extraction, and implement the second phase of Hubert. These are the papers that we were inspired by during our research, and thank you so much for listening.